But you can ask some questions if you have any. Do you have any questions? So can you see the screen?
Yes.
Yes.
So I think we stopped. Where did we stop last time? I think it was here. Do you prove that the center is a subgroup?
Yes, yes.
So we did this. And you had an exercise here to do. So I'm assuming you have tried to solve this problem, finding the center. So we can start from here. So you recall the homomorphisms and so on. Here we have a map from, if you don't recall, please find time to watch the videos again. The videos are available for you to watch. So if there's anything that is not clear, you can make an effort to go back and watch them at your own pace. And if you have questions, you are free to ask in the class. Simply put on your mic when you have a question, then you ask. I think we still have some people trying to join. Let's allow them so that we can continue. Yeah. So so now we can start. Let me set up the slide, the presentation mode. And here we have the theorem. It says the following. If you have a homomorphism between these two groups, G and H, then we make the following claims: that the kernel of the homomorphism will be a subgroup of G. Remember, the kernel is a subset of G, and therefore the claim here is that it's also a subgroup of G. And then the image of the map is a subset of H. And the claim here is that it's a subgroup of H. So you have to be careful where these two sets belong. You have to keep track of that. So we shall prove that first that the kernel is a subgroup, then we check. We prove that the image of the map is also a subgroup. So to prove that it's a subgroup, first of all, we confirm that the kernel is not empty, because the identity element is always in the kernel. So we shall denote the identity of the group H by E prime. So that's what we shall have. So for us to show that the kernel is a subgroup, there are two things we need to show. One is to, well, here we'll pick one. There are two ways we can do this. One is to use a first method, where we check that it's closed and every element in the kernel has an inverse in the kernel. So the second one is just to show that the product of, you have two elements X and Y in the kernel, the product of the first and the inverse of the second will also be in the kernel. This is also sufficient to prove that the kernel is a subgroup. So this is what we shall do. Pick two elements in the kernel. We need to show that the product of the first and the inverse of the second element will be in the kernel. So to check that it's the kernel, we simply check whether this element is mapped onto the identity in H. So we apply the homomorphism to this product, and we have, using the properties of the homomorphism, we can split this into the image of X times the image of Y inverse, and the inverse we know can jump out. Now we know that X and Y are both in the kernel, So the image of X must be the identity in H. The same with the image of Y, it must be the identity of H. And the identity, the inverse of the identity is just the identity. So that's why we have the inverse of in H times the inverse on H, which is in H, which is equal to E prime, the inverse in H. So we have shown that the image of this product, XY inverse, is equal to the identity in H. So that simply means that that product, X and Y inverse, are in the kernel. But now this is all we need to show to prove that the kernel is a subgroup of G. So that solves our first case. Any questions on this? Isaac, do you have some questions?
No.
Okay, so we can move on to the second part to check that the image of the map is, or maybe we can illustrate this to the diagram first before we move on. So if you have a map from G to H, this map is given here. This diagram shows the kernel of G. So the kernel is a subset of this group G, and it consists of all those elements in G which are mapped onto the identity in H. So what you have just shown is that this subset of G is a subgroup. So let's move on to the image. So now the second bit is to show that the image is a subgroup of H. So we need to pick any two elements in the image, and we show that the product of the first element in the image and the second element in the image, the inverse of the second element in the image, this product will belong to the image as well. So now if two elements are in the image, we should be able to find the pre-images, that is X and Y in G. So they can only be in the image if they have some elements X, Y, and G, which are mapped onto alpha and beta. That's by definition. Otherwise, they will not be in the image. So we are guaranteed to find these two elements in G, X and Y, which will be the pre-images of alpha and beta, respectively. So if we multiply alpha and beta inverse, we can replace alpha with the image of X and replace beta with the image of Y. This is what we have. And we use the fact that this map is a homomorphism. So this these two are the same. I think this next step should have had, the inverse should have gone into the bracket, but I think you can figure that on your own. Then there's an extra bracket here that is not needed. This first bracket is not necessary. So you can put them back together again because this is a homomorphism. So this is possible. But we know that since X and Y are in G, Y inverse will also be in G. So X, Y inverse is an element of G, which is mapped onto alpha, beta inverse. So we have found a pre-image for this alpha, beta inverse. There's an element which is X, Y inverse here, which is mapped onto alpha, beta inverse. So alpha, beta inverse is definitely in the image. Or any pair of elements that you pick from the image. And that means the image is a subgroup of G, of H. So here we have G on this side, and we have H on this side. If you have alpha and beta here, this shaded part is the image of the map. The image of a map can be the whole group or can just be a subset of the group. So if you get the pre-image of alpha and beta inverse, it turns out to be XY inverse. So alpha beta inverse turns out to be the image because we can find a pre-image for it in G. Are we together up to that point? Hello? Are we together? You can hear me?
Yes, you can.
Yes.
Good. Fine. So that is settled now. Here is another theorem. It says the following. Let H and K be subgroups of G. It should be subgroups of G. Then the set HK, which is made up of this kind of products, it's made up of the product HK, where H is picked from the subgroup H, and the small k is picked from the subgroup K. So to construct this set simply means you have to get all such products, the distinct ones, HK. So HK, this HK we are claiming is a subgroup if and only if HK is equal to KH. So this does not mean that the groups commute. It just means that these two sets are equal. Because the commuting, the group will only be commutative if these small ones, these elements of G commute. Here, this does not say anything about the elements commuting. It simply says that these two subsets, these two sets, HK and KH, are equal. So KH will simply be reversed here. This set KH is simply the reverse of this. You switch the first element to be from K and the second element to be from H. And all such products will be the elements in this set. For KH, it's a similar. Are there any questions on this? So this is an if and only if theorem. We have to prove the theorem and its converse. The first thing is to assume that this set is a subgroup of G. And if it's a subgroup, then this must happen. HK must be equal to KH. The second thing is to assume that HK is equal to KH and show that that implies that HK must be a subgroup. Any questions? So let's go through the proof. So the first thing is to assume that HK is a subgroup and show that if it is a subgroup, then HK should be equal to KH. So assuming it's a subgroup, HK, any pair of elements you pick, A from H and B from K, we will have that BA is the same as A inverse, B inverse, inverse, right? But this, since HK is a subgroup, these elements must be in HK. So we have picked an element from KH. BA is an element from KH, and we have shown that it's contained in HK. The reason we can make this statement is we know that HK is a subgroup. So the product of any elements in HK will be in HK, and the inverses of any element of HK will be in HK. So this thing must be in HK. We picked an element from KH because B is from K and A is from H. So BA is from K, capital KH. KH is this one. And we have shown that any element from this KH turns out to be in HK, and therefore it means KH must be contained in HK. So this is true since HK is a subgroup. Our aim is to show that HK is equal to KH. So we have one more inclusion to show. We have shown that KH is contained in HK. What's left is to show that HK is contained in KH, and therefore they must be equal. So let's pick an arbitrary element from HK. Now already we have assumed that HK is a subgroup, and therefore the inverse of P must also be in HK, right? And therefore you can write it as a product of an element in H and some element in K. Again, remember the reason for this is that HK is already assumed to be a subgroup. So if you pick any element from HK, its inverse must be in HK. And any element in HK is written in this form as a product of some element from H and element from K. Okay, so let's see. So we need to find P. P itself will be the inverse of XY. That's the inverse of the inverse of P. But this is the same as Y inverse, X inverse. We know that Y is from K, and K is a subgroup, so Y inverse will still be in K. We know that X is from H, and H is a subgroup, so that X inverse will still be in H. So we've been able to write P, which was from HK, as a product of some element from K and an element from H. So this element is definitely in KH. So we're picking any element from HK, it turns out to be also in KH. So we can conclude that HK is a subset of KH. Now using these two results, 1 and 2, we conclude that HK is equal to KH. So what have we proved? We have proved that if HK is a subgroup of G, then this condition must be true. HK will be equal to KH. Any questions on this? You can still hear me?
Yes, you're getting.
Yes.
Okay, so I will move on to the next part of the proof. So the next part of the proof is to assume that this condition holds, and if it holds, then HK must be a subgroup of G. So we start with that assumption that HK is equal to KH. So let's pick any two elements, A and A prime from H, and B prime from K. So we want to construct we want to pick two elements from HK, right? The aim is to show that HK is a subgroup, so we must show that it is closed and that the inverse of any element in HK will also be in HK. But that should be implied by this condition. We have to make use of this condition that HK is equal to KH. So these are two elements from HK. The first element is AB, and the second element is A prime, B prime, right? Using the associative property, we can write this as, we can put the brackets in here. This element B, A prime, is from KH. I skipped a step. This element is from KH, but you can follow. This element BA is from KH, but since KH is equal to HK, this element BA must also be in HK. So I can replace this with a bigger set, which is HK itself, in which it belongs. And this whole element will be an element of this set. Now what we have here is a set. It's not an element anymore. And now this is just repeated. So this should be out. I can replace, since A is from capital H, the subgroup, I can replace A with H, and this set now will be a subset of this. I can also replace B prime with K, and the set I create here will contain this set. But H, because of closure, I will not go into the proof for this. H will just be equal to H itself. You can check that in your own time. The same thing with KK will be equal to K, because K and H are both subgroups. So this now reduces to just HK. So we picked two elements from HK, and we have shown that their product is in HK. So we now need to pick another element, AB, from HK, and show that its inverse will also be in HK. So from what we learned earlier, AB inverse is the same as B inverse, A inverse, which belongs to KH. The reason for that is that B is from K and A is from H, so this belongs to KH. But we have already made the assumptions that HK is equal to KH, so we can say KH will be equal to HK. And therefore, the inverse of this element from HK will also be in HK. And therefore, that guarantees that HK will be a subgroup. So we have shown the theorem and its converse be true. Any questions?
Nope.
Okay, so let's move on. So we now shift to a new gear. We will be talking about the cyclic groups. So, but before we define the cyclic groups, we will play around with some ideas. So let G be a group, and let's pick an element G from the group G. We can create a set we call the set H, which consists of all powers of G. So all elements of a form G raised to K. So that's G multiplied by itself K times, where K is some positive integer. No, where K is just an integer. If it can also work if K is negative, because I will explain that notation later. But it doesn't matter whether K is positive or negative. The reason for that is we need inverses as well. So GK, all elements of the form G raised to K will be in this set H. So let's pick any two elements from the set H. So A and B are from H. And since they are from H, it means they must be written as powers of G. That's their form. Any element in here is simply a power of this fixed element, G. So we write A as G raised to K and B as G raised to L, where K and L are integers. So we need to check what is AB inverse. AB inverse is the same as GK raised to G minus L. This is L. And this is the same as GK minus L, which is still a power of G, right? So the product of A and the inverse of B turns out to be still a power of G, and any power of G belongs to H. So this product belongs to H. And using the second method of checking that a subset is a subgroup, we can conclude that H is indeed a subgroup of G. So if you pick up any element in the set, you can construct a subgroup of G. Any element different from the identity. The identity will still construct one, but it's not a very exciting group to look at. It has only one element. But if you pick any element in a group G, you can always construct another subgroup, a subgroup of G, by taking all powers of that element. So this is another way to construct subgroups of a group. Anytime you want to construct some subgroups, simply pick an element and get all the powers of that element. So the assumption here is that the binary operation is written multiplicatively. We shall look at a situation where what notation we shall use when the binary operation is written additively in a minute. So based on what we have seen there, we can define a cyclic subgroup. So if H is equal to this set, H consisting of all powers of G, is called the cyclic subgroup of G generated by this small g. So this element G that is fixed is called the generator of the cyclic subgroup. So we shall denote the cyclic subgroup generated by, this should be small g, not capital G. So the cyclic subgroup generated by the small g will be denoted by this G with square brackets around it. Some books use a different notation. Some books will use angle brackets. Some will use square brackets. Just be aware of the notation. If you choose to read a textbook, keep track of the notation used in the textbook. But for our class, we shall stick to this notation. So don't use any other notation for our class. This is the notation we shall use to denote the cyclic subgroup generated by this small g. So it can happen that you have an element in the group, say A, that generates the whole group. Then in such a case, we call the group cyclic. So if it turns out that this H is equal to the whole of G, then that group G will be called a cyclic group. So note the difference between cyclic subgroup and cyclic group. A cyclic subgroup refers to a subgroup of G. And then a group will be called cyclic if it turns out that one of the cyclic subgroups is actually equal to the whole of G. Is that making sense? So the only correction you need to keep track of is in this third bullet here. The cyclic subgroup generated by the small g. It should be a small letter g. Be denoted by this notation where you have g with the square brackets around it. Any questions on that? Again, maybe I should check if you can hear me. There's no response.
Yes, we are hearing.
Okay.
Yes, we can hear you. Excuse me, sir.
Yes.
There is someone who is saying, please, you can let her in.
Okay, they need to learn to be punctual.
Excuse me, sir.
Yes.
Can you scroll down? Yeah, I want
You're saying? Someone was asking a question. You forgot the question, or you have answered your question.
I've answered it.
Oh, okay. So here is a remark about the binary operation when it's written additively. Then the cyclic subgroup will consist of all multiples of A. Right? So NA in this case simply means A added to itself n times. So instead of having powers, what you have are multiples. You recall in the definition for cyclic subgroup, we had G raised to K. So we had powers, since the binary operation there was assumed to be multiplicative. But here, if you choose to write the binary operation additively, then the cyclic subgroup generated by an element A will simply consist of all multiples of A, where A is an integer. So if n is positive, then you simply have the n-fold sum like this. But if you have if it's a negative integer multiplied by a, if it's a negative multiple of a, it simply means you add the inverse of a to itself n times. So the cyclic subgroup, when you have an additive group, will consist of all multiples of the element of the generator. So there are situations where it's convenient to use this notation, especially when the group is written additively. And there are also situations where it's convenient to write the cyclic subgroup multiplicatively. So any questions on this?
No.
Can you please turn to the other page, to the page before this one, to the slide?
Yeah.
Yes.
You have a question on this page?
Yeah, there's a in the at the bottom it says cyclic group, and the other one which you've learned is one of the top is a cyclic subgroup.
Yes.
So you've used one to define another.
What is your question? So a cyclic subgroup, to construct a cyclic subgroup, you simply need to pick an element from the group and find all possible powers of that element, right? That will give you a cyclic subgroup. So they can be a situation where you find one element which generates the whole group. So it's not guaranteed that all powers of G will give you the whole group, right?
Yes.
You will get a subset, most likely. But there are situations where you can find an element which gives you the whole group again. If you get all powers of that element, you end up with the whole group. So if there's such an element in a group, then that group is called cyclic. You can also have situations where none of the elements in the group will generate the whole group, and then that will not be a cyclic group. But even if a group is not cyclic, it can always have cyclic subgroups, because you pick any element in the group and get all possible powers of that element, and you will have a cyclic subgroup of the group. So the group doesn't have to be cyclic, but you can always have cyclic subgroups. You will always have cyclic subgroups. Does that make sense?
Yes.
So this only applies if there's an element that generates the whole of G. If there's no element that generates the whole of G, then the group is not cyclic. Okay, see, so we have already gone through this, the additive notation. So here the assumption is that n is a positive integer. Maybe I forgot to say that. If n is a positive integer here, then this multiple of a simply means a added to itself n times. So this was written backwards. So consider this following, B3, and we pick A in B3. I think we had defined A as this map. The rotation through, was it 120 degrees? So you can obtain all possible powers of this L map A in B3. Remember, the binary operation was composition. If you compose A with itself, you get A squared. You compose A with A squared, you get a cubed, but we know that a cubed in D3 is equal to the identity element. So this gives us all the possible powers of A. There are only 3 of them that we can find. Any other power will coincide with one of these. For instance, if you take A raised to 4, A raised to 4 is the same as A, because it's the same as A cubed multiplied by A, which is just EA. So any other power of A will coincide with one of these 3. You can't get anything outside those 3. So based on that, we can make the following conclusion, that the cyclic subgroup of D3 generated by A will consist of these 3 elements: the identity element, the A itself, and A squared. So this gives us a cyclic subgroup of D3 generated by A. You can also check that this element A squared will generate the same cyclic subgroup. If you try to get all possible powers of A squared, you will end up with the same. You can try it even now. If the first element would be A squared, then multiply A squared by itself, you get A power 4, A raised to 4, which will be equal to A. So we already have A squared and A. And then raise A squared to 3, then you'll have A raised to 6. A raised to 6 is the same as A cubed multiplied by itself, which is the identity multiplied by itself. So again, you end up with A squared, A, and E. So A and A squared will both generate the same cyclic subgroup of D3. So you will need to refer back to your notes, earlier notes. These elements of D3 are described in the previous in a previous class. So go and find out what A is and what A squared is, and try to get all possible powers. So there was a reflection B in D3, the dihedral group of degree 3, and the cyclic subgroup generated by B will simply be E, will consist of just B and E. This is because we know that B is its own inverse, so that B squared will be equal to the identity element. So any other power of B will coincide with one of these 2. It will either be E or B. So no matter how many times you keep raising B, you won't get anything different from these 2. So you only pick the distinct ones. There is no need of repeating E and the B again, E and B. It's because it will be repeated if you keep getting higher powers of B. So that's the highest, the most you can get. And the cyclic subgroup, therefore, generated by B will consist of just these 2 elements, E and B. This square bracket should not be there. This should be the curly brackets denoting a set. These should not be square brackets. I will fix that. So if you pick all the elements of D3 and try to generate the cyclic subgroups, none of them will generate the whole of D3. You can check this yourself. We already tried with A. It only generates 3 elements. You know, D3 has 6 elements. So A does not generate the whole of D3. We have also seen that B, the reflection, only generates a subgroup with 2 elements. So all the other reflections will also generate subgroups with 2 elements. You can check this yourself. And that means none of the elements in D3 will generate the whole group. And that means that the dihedral group of degree 3 is not a cyclic group. So the gentleman who was asking about a cyclic group and a cyclic subgroup, maybe this will make it clearer. So let's look at an example of how we can construct the cyclic subgroups. So we will consider the group Z8. When we say Z8 without mentioning the binary operation, what it's automatically means addition modulo 8. Because under multiplication modulo 8, it will not be a group. So anytime we say Z8 or Zn without mentioning the binary operation, the assumption is that we shall be using addition modulo n, in this case, addition modulo 8. So let's try to get some cyclic subgroup for Z8. If you pick, since the group is additive, we shall be looking at multiples instead of powers. So if we pick an element 2 from Z8, we can get all possible multiples of 2. So the first one is just 2 itself. 2 plus 2 is the same as 2 times 2 in this case. It will be equal to 4 modulo 8. Remember, this addition is not the usual addition, it's addition modulo 8. So if you add 2 to itself 3 times, you have 2 plus 2 plus 2, you will get 6 modulo 8, that is just 6. If you add 2 to itself 4 times, you will get 8, but 8 is equal to 0 modulo 8. The remainder when you divide 8 by 8 is 0. Now 0 is the identity element in Z8. So it means if you get any more multiples of 2, they will coincide with one of these, either 2, 4, 6, or 0. And that means that the cyclic subgroup of Z8 generated by 2 will consist of these 4 elements. You have exactly 4 elements, that is 0, 2, 4, and 6. That makes sense?
Yes.
So we can also check the cyclic subgroup generated by 4 will consist of only 2 elements, that is 0 and 4. And you can check that 4, if you add 4 to itself twice, you will get the identity element. 4 plus 4 is 0 modulo 8. So if you pick 1 as your element and generate the cyclic subgroup using 1, it turns out that you generate the whole group. You can check this. If you add 1 plus 1, you will get 2. 1 plus 1, add to itself 3 times, you get 3. Add 1 to itself 4 times, you get 4, and so on until you add 1 to itself 7 times, you will get 7. And 1 to itself 8 times will give you 0. So it turns out that if you use 1, you generate the whole group. So we have found an element in Z8 which generates the whole of Z8. And in this case, we can say that Z8 is a cyclic group, and the generator of the cyclic group is 1. So there can be more than one element that generates the whole group. So in your own time, you need to check that 3, 5, and 7 will also generate the whole of Z8. So we will have exactly 4 generators for the whole group in this case. 1 was the obvious one. Then we have 3, 5, and 7. So do you notice any relationship between these generators and the number 8? We have the generators as 1, 3, 5, and 7. What do you notice? What is the connection between them and the number 8?
They are prime. They are
Co-prime, yes.
They are GCD.
Or relatively prime.
Yes.
Yeah, if you pick any other number that is not co-prime, for instance, 2 is not relatively prime to 8, you can see 2 generates a subgroup of order 4 with only 4 elements. It does not generate the whole of Z8. The same with 4. If you pick 6, I think will also generate this. Because 6 plus 6 will give you what? It will give you 4. And then 6 plus 6 plus 6 will give you 2. And 6 added to itself 4 times will give you 0. So 2 and 6 will generate the same subgroup. So this subgroup here is generated by 2 and also by 6. So you have seen that all the other elements, 2, 4, and 6, which are not relatively prime to 8 cannot generate the whole of Z8. So the ones that generate the whole of Z8 in this case are just 1, 3, 5, and 7. So as you noted, in general, Zn is a cyclic group, and it will be generated by the elements which are co-prime to n, elements whose GCD with n is equal to 1. And you can see that as well in our example. The GCD of 1 and 8 is 1, 3 and 8 is 1, 5 and 8 is 1, and 7 and 8 GCD is 1. Any questions? So it's important to write these things down. If you don't write these things down and try them out yourself, next time you look at them, they will look like a total stranger to you. So make sure you pull out your exercise book and your pencil and pen and a cup of tea or coffee as you write these notes down. Ama mnakunywa uji? Even porridge is okay. Just pick your favorite drink, soft drink in particular. So here is another example. There is this set that consists of the fourth roots of unity. I think you know how to find the fourth roots, the nth roots of a complex number. Did you do that in basic mathematics?
Yes.
Oh, okay. That is good. So if you these are all the fourth roots of unity. The fourth roots of unity simply means the fourth roots of 1. So it consists of all complex numbers whose fourth power is equal to 1. So I here is simply the imaginary unit I squared, which is defined as I squared is equal to -1. So this is actually a group under the multiplication of complex numbers. You can easily check that. It's a group with exactly 4 elements. So let's see if we can extract some cyclic subgroups. You can see that a cyclic subgroup generated by -1 will consist of these 2 elements, 1 and -1. If you keep getting powers of -1, you won't get out of any of these 2. You won't get any other number outside these 2. So all possible powers of 1 will either be 1 or -1. And therefore the cyclic subgroup generated by -1 will consist of these 2 elements, 1 and -1. Let's see if we can generate some more. Now this bullet was not supposed to be under that. Anyway, I'll fix that. If we try to obtain the cyclic subgroup generated by this imaginary unit I, we get the whole group. So how do we get it? We start with I. So I squared will be equal to -1. What about I cubed? What is I cubed?
-I.
Correct. So -I. Then I raised to 4 will be the identity 1.
1.
So if you keep getting higher powers, you won't get anything outside these 4. Any other power will coincide with just one of these 4 elements here. The same will be true for -I. -I will generate the whole of this group C4. So this group has 2 generators, that is I and -I. The other 2 elements, 1 and -1, cannot generate the whole group. So that means we conclude again that this is a cyclic. This is a cyclic group because you have found some elements, 2 elements actually, in the group that generates the whole group. So we can call this a cyclic group. So I think there was a problem in the. This is just a conclusion of this. It's not a different example. So it's the same example. This should go actually. So C4 is simply a cyclic group whose generators are I and negative I. We have seen that up here. Anybody with ideas, comments?
Is I cubed equals to 1? I mean, is I cubed equals to -1 or I?
You're asking me, or have you tried it? You need to try it. By now you should be able to do that computation yourself.
I thought that the answer should be -1.
I squared is -1, not I cubed. So look, I squared is -1, right? So how do you get I cubed? Multiply this by I, right? So multiply both sides by I. You'll have I cubed on this side. On this side, what will you have? So -1 times I will give you what?
Negative I.
So how
Negative
are you getting -1 when you get I cubed? Maybe you can.
Yeah, I've gotten it right. Thank you.
Hello? Is your question now fully answered? You have understood how we get I cubed is equal to -I.
Yeah. Thank you. Excuse me, sir.
Yes.
Yes. Okay. I have a question. When we are
Ask.
when we are talking about the generators of a cyclic group, are we talking of the generator which will generate all the elements of that certain group?
That's exactly what we said.
Okay. Thank you.
So if it's a cyclic group, there must be some elements in the group which can generate the whole group. Otherwise, it is not a cyclic group.
Okay.
So
Thank
those
you.
elements that generate the whole group are called generators
Yes.
of the group. The subgroups also, the cyclic subgroups also have their own generators.
Yes.
They generate the cyclic subgroups.
Yes, I got it. Thank you.
Okay. So here is another example of an infinite. We have been looking at finite subgroups. Here is an infinite subgroup, an infinite group rather. Here's an infinite group, cyclic group. The generators for this cyclic group are 1 and -1. Remember again, this is an additive. The binary operation is written additively. And therefore, instead of powers, we are considering multiples. So any integer can be written as a multiple of 1 or -1. So those are the only two generators of this group of integers under addition. So it's an infinite cyclic group, and the generators are 1 and -1. Because any integer can be written as a multiple of 1 or a multiple of -1. So for instance, if I want -5, I will multiply 1 by -5, and I will get -5. Is that making sense?
Yes.
So remember, when we write a binary operation additively, we talk of multiples instead of power. So if you fix a natural number, any positive integer, then all multiples of that integer also form a subgroup of Z, and the generator would just be N in this case. So for instance, these all multiples of 2 for the even numbers, if you like, will form a subgroup, a cyclic subgroup of Z, and the generator is 2. So you can also create another subgroup using 3, 4, 5, and so on. So here is an exercise for you. You can do it in your own time. Maybe you should note it down. Or we'll share the video again, but maybe it's a good idea to note it down now. Prove that every cyclic group is an abelian group. And the second part is you need to give an example of an abelian group which is not cyclic. So that's some work for you to do. You don't need to do it now. But if you have an answer now, you can share with us. So does anyone have an answer? Is there anyone who can prove that any cyclic group will be an abelian group? Or does anyone have an example of an abelian group that is not cyclic? Abelian simply means commutative. So for this second one, I suggest that you go and study the symmetries of a rectangle, the Klein 4 group. So that will give you an example of an abelian group that is not cyclic. It's the symmetries of a rectangle, which is not a square, consists of only 4 elements, and all the elements different from the identity are of order 2, and therefore cannot generate the whole group. So go and have a look at that. The Klein 4 group, which is basically the symmetries of a rectangle, which is not a square. So here is a theorem. It says every subgroup of a cyclic group is cyclic. So what this claims is the following. If you have a group and you know that a group is cyclic, then you can find all the subgroups of that group by just picking elements from the group and generating subgroups using those elements. Because once you know that the group is cyclic, then all the subgroups will be cyclic. So let's prove this. So, but the converse is not necessarily true. It's possible to have a group where all the subgroups are cyclic, but the group itself is not cyclic. That is possible. So, converse may not necessarily be true. If a group, it's possible for all the subgroups to be cyclic, yet the group itself is not cyclic. So, to prove this, first of all, we assume that the group is cyclic and show that all the subgroups must be cyclic. That's what this says. So just assume that the group is cyclic and use that to show that any subgroup in the group must be cyclic. So let's assume that G is generated by A, where A is some element of G. Already assuming that G is cyclic means it has a generator which generates the whole group. And now we pick any subgroup of G, and we need to show that this subgroup must be cyclic. In other words, we can find one element which generates the subgroup. So since H is picked from elements in G, it's a subset of G, then all elements in H must also be powers of A. But since H is a subgroup, if A raised to n is in H, then its inverse will also be in H. So the inverse of A raised to n is usually denoted as A minus n. It's just the inverse of A raised to n. Because the subgroup, the inverse must be in H. So it means there must be some positive power, because if n is less than 0, then minus n will be positive, and vice versa. If n is positive, then minus n will be negative. But we're interested in the positive one. So this guarantees us that there will be at least a positive power of A in H. So let's assume this positive power of A in H is I, A raised to I. And there may be more than one positive power. So we can definitely find the smallest positive integer, M, such that we call it M, such that A raised to M is in H. So this is possible because of the well-ordering principle of the natural numbers. So any subset of the natural numbers will always have a least element. So we assume that we showed that it's possible to find some positive powers of A. So out of all the positive powers, since they are natural numbers, it's possible to find the smallest one. And let's fix that smallest one to be M. That's the smallest integer, positive integer, such that A raised to M belongs to H. So let's pick any other element in H. We call it A raised to N. So we need to show that any other element in H can also be written as a power of A. So if we apply the division algorithm to these two, M and N, we can always write them in this form. And write them N is equal to MQ plus R, where R cannot exceed M. It can be 0, but cannot exceed M. Now, we can therefore write this power, A raised to N, as A raised to MQ plus R. And we can split it into two like this, A raised to MQ and A raised to R, which is in H. So the only way this can be true, we already know that AMQ is in H, because A raised to M was picked to be in H, so any power of A raised to M would still be in H. And the only way this can be true is if AR is also in H. The reason for that is because H is a subgroup. So we make that conclusion that AR is in H. But now we see that R is strictly less than M. So that poses a small problem, but we can solve it. It means R can only be equal to 0. It can't be any positive number bigger than M. So the only way you can be in H and be smaller than the power of H can be of A rather can be in H, and that power is smaller than M is if that power is equal to 0. Otherwise, it will contradict the minimality of M, because earlier on we said M is the smallest positive integer such that A raised to M belongs to H. So if any other smaller number behaves the same way, it only has one option, but to be equal to 0. Otherwise, it contradicts the fact that M was the smallest positive integer. So R has only one option here, can only be 0. And since it is 0, then it means A raised to N can just be written as A raised to MQ. Because R is 0, we're just left with MQ. And we have this A raised to N can be written as a power of AM. So this AM, which was in H, is an element in H. It's possible to write any other element in H as a power of this element, AM. So that means we have shown that H, the cyclic subgroup, will be generated by this element A raised to M. And H was any group, any subgroup. We picked it arbitrarily. And that means any subgroup you pick must be cyclic, and you can find the generator. So this not only tells you it is cyclic, it actually shows you the generator of the cyclic subgroup. So that's a conclusion. Any subgroup turns out to be cyclic, and we found the generator to be a raised to m, where m is the smallest positive integer, such that a raised to m will be in the subgroup H. So we comfortably conclude that every subgroup of a cyclic group is cyclic. Any questions? So this one requires you to spend some time on it. A lot of these things require a lot of repetition for them to stick. So I encourage you to find time and look at this. Any questions? You can hear me?
Yes.
Yes, can hear you.
But you have no questions. So, like we said earlier, it's possible to find a group which is not cyclic, yet all its subgroups are cyclic. An example is D3. All the subgroups of D3 are cyclic, but we saw earlier that D3 itself is not a cyclic group. I hope that makes sense. Does this make sense to everyone? So we just found an example here. There are many other examples. So we proceed now to the next section. But you can also, what we can do, we can give you a 3-minute break. Then we start again. Is that okay?
Yes.
Yes.
3 minutes. We resume at 9:30.
Okay.
Okay, so we are back again now. Merudi.
Yes, tuko.
Good. So
Yes.
let's continue. So now we move to another subtopic. We were just talking about the cyclic groups. Now we'll talk about the order of an element, and again we shall connect this with cyclic groups later on. But I think this is the last bit we will do, the order of an element. So let G be a group, and pick an element A in G. So if A raised to n will be equal to the identity element for some positive integer n, we say that A is of finite order. As long as you can find some positive integer n such that A raised to n is equal to the identity, then we can conclude that A is of finite order. If that doesn't happen, we say that this element is of infinite order. We shall illustrate this shortly. So if we have an element of finite order in a group, and if we find the smallest positive integer such that A raised to m is equal to the identity, so the keyword here is the smallest positive integer such that A raised to m is equal to the identity, then we say m is the order of this element A. Are we together?
Yeah.
Yes.
Okay, so let's continue. So we set up some notation. So we shall denote the order of the element A by this, just this small circle, then the A in brackets. So this keep track of this notation. If you are, the order of A would simply be denoted by this. This would be the shorthand we shall use. So now there's usually some point of confusion because the word order sometimes is also used elsewhere. So maybe we can clear that up. Yeah. So when you're talking about a group, the order of a group is simply the number of elements in the group, right? Here we are talking about the order of an element in the group. So don't confuse those two. The order of a group is simply the number of elements in the group. But the order of an element in the group is the smallest positive integer, let's say m, such that A raised to m will be equal to the identity. So don't mix those two. Are we together? There can be situations where the order of an element can be equal to the order of a group. That is possible, but they are not the same thing technically. One refers to an element, just the order of an element as defined here, and then the order of a group. If you see any place where this is mentioned, the order of a group, there's nothing complicated here. This is simply the number of elements in the group, the cardinality of the group. Is that okay? So this remark is really important because I see previously in previous classes I've seen a lot of confusion arising from that. So make sure you take note. Don't confuse the order of a group and the order of an element in the group. So let's look at some examples. So in the dihedral group of degree 3, this element in the group A, if you raise it to 3, you get the identity, and B squared will also give you the identity. So there's no smaller integer when A raised to that integer will give you the identity. The same for B. You can't find a smaller integer which satisfies this equation. So that means the order of A, a smaller positive integer that is. So that means the order of A is 3 and the order of B is 2. So those two elements have that order. You can check also that the order of A squared is equal to 3. A squared is also one of the rotations in this dihedral group. So let's check in Z8. Here the group is written additively. So again, if you add the elements, if you don't get powers, you get multiples of an element. So if you pick 2 in Z8, if you add 2 to itself 4 times, you will get the identity. The identity is 0. So then the order of 2 is 4, because the smallest number of times you have to add 2 to itself to get the identity is 4. So you can check 1 has order 8, because if you add 1 to itself 8 times, you get 0, and you can't get a smaller positive integer that works. The smallest that works is 8. So the order of 1 is 8. The same is true for 3, 5, and 7. They all have the same order, equal to 8. Later on, we shall see how you can determine the order of when two elements have the same order. So let's go to Z5. So here, notice that 5 is a prime number. This was picked deliberately. Every non-zero element in Z5 is of order 5, actually. You can check that if you add 1 to itself 5 times, you will get 0. The identity in Z5 is 0. And remember what we said, I say Z5 without mentioning any binary operation, that's automatically addition modulo 5. The binary operation is addition modulo 5. So the order of all the non-zero elements in Z5, I think this should be 4, not 5. This should be order of because Z5 consists of the elements 0, 1, 2, 3, and 4. There's no 5 in Z5. 5 is the same as 0 in Z5, so we don't include it. So this should be 4. So the numbers 1, 2, 3, and 4 are all of order 5. So that is because, and this is true whenever this is a prime number. So for instance, if you have Z7 or Z11, all the non-zero elements will be of the same order as the group itself. So Z5 has 5 elements, and every non-zero element also has the same order. So these are situations where I told you it's possible sometimes for the order of an element in a group to be equal to the order of the group, but it's not always the case. And we shall see later on, maybe not in this class, how that works better. So if you consider the group of integers, again, anytime we mention the group of integers without mentioning the binary operation, it means we are referring to the group, the set under addition, the usual addition. Because we know the integers will not form a group under multiplication. So if I don't mention the binary operation, what this simply means is addition. So we make some claim here that every non-zero integer in this group is of infinite order, because if you pick any non-zero integer, there's no number of times you can add it to itself to get the identity. The identity is 0. So for instance, if I pick 2, No matter how many times I add 2 to itself, I will never get 0. So in Z here, the addition is just a normal addition. Z5 and Z8 is where we had addition modulo 8 and modulo 5 respectively. So here is here is one more example. There's someone whose mic is on. Here's one more example. We pick someone whose mic is on. I don't know why you're keeping it on.
Excuse me, sir.
It's interfering. Huh?
Excuse me, sir.
Can you speak into the mic? Your voice is a bit. You are hearing the noise more than your voice. Yeah, I thought someone had a question.
I have a question.
Yes, ask.
From that previous example yes, now that 5, that equal to 5 and 8, are they the elements of order 1, order 2, and order 3, or order 4 in Z5?
I don't understand your question. Let's go back to the notation.
Yes.
Pay attention. Look at this line here. The order of an element in the group, the element is A, would be denoted by this. Is that clear?
Yeah.
So let's go back to this. So what is your question again?
I was asking that 8, in Z8 you say that there are elements of order 2. Elements of order 2 are 4, since 2 plus 2 plus 2 is equals to 0. And order 1...
There's no, this, please, let's go back to the definition again. Please pay attention. The order of A is denoted by this. So if I have this circle here and A in the brackets, this thing means the order of A.
Yes.
Yes. So when I go back here, you see, let's look at the first example. The first example says the smallest positive integer here is 3, such that A raised to 3 will give you the identity. So it means the order of A here in B3 is equal to 3. Does that make sense? Hello?
Yes.
The same is true here. The order of B is equal to 2 because 2 is the smallest positive integer such that B raised to 2 is equal to the identity. It's important that you get these definitions correct. Otherwise, you will not be talking properly. So in Z8, 2 is an element in Z8. So when I write this circle here and the 2 in brackets, what this thing here means, the order of 2.
Yes.
The order of 2 is equal to 4. I'm not saying this is an element of order 2. Okay? The order is this 4. This means the order of 2 is equal to 4. Okay, but now in Z8, we can't get powers. You have to get multiples. So if the binary operation here was multiplicative, this would be 2 raised to 4. But since we are working with an additive binary operation, we get the multiple of 2. Keep getting multiples of 2. So add 2 to itself 4 times, you will get the identity, which is 0. So if you were to write this multiplicatively, you would write 2 raised to 4 is equal to 0. So that the order of 2 will be equal to 4. I don't know if that is making sense now.
Yes.
So what was your question again? Because you can only ask when you're fully understood. Rather, your question is meaningful when you're fully understood the notation. So now you can ask the question.
I was asking that now, for example, that order of 2 is equals to 4.
Yes.
That means that in Z8, we have 4 elements of order 2.
2 is an element in Z8, right? So here we are not talking about any other element other than 2. We are picking 2 and finding the order of 2. If you want to know how many elements of order 4 are in Z8, simply go through the elements in Z8 and keep adding them and see if you'll get any other element of order 4. So that's how you find out how many elements. Z8 has only 8 elements. That should be very easy for you to check. So don't make statements which you can check if you have not checked them. So there's nothing here that says there are 4 elements of order 2. The only thing here is that we are saying the order of this element 2. 2 is an element in Z8. Its order is equal to 4. It's very important that you understand the notation. Otherwise, your question will not make sense. So if you are to write this in English, we will say that the order of 2 is equal to 4. If you write this as a sentence. And that's how you should learn to read mathematics. Read it as an English sentence. So are we on the same page now?
Yes.
So can you now ask your question?
I've now understood it.
You have understood, okay.
Excuse me?
Yes.
That you've not given the order of 4. Can you say that the order of 4 and Z8 is 2?
Yes, now you should be able to get it yourself.
Wow, thank you.
Don't wait for me to give all of them. I'm leaving some of the work for you. You know, the teacher is supposed to do 25%. Ama namna gani? Is that a fair deal?
90%.
90. Ai, nitaongeza school fees. Okay, but you don't wait for everything to be done for you. Once you know how to find the order of elements, you've seen how we can find the order of 2. Now, in your own time, find the order of 4, find the order of 6, so on. So you simply add the number to itself until you get the identity that will give you the order. So here we made a correction. This should be 4, not 5, the order of 4. So all the non-zero elements in Z5 have the same order, and that is 5. So how you find the order is simply by keep adding the number to itself until you get 0. The earliest point you get 0, that gives you the order. The same thing we have done for 2 here in Z8. Always remember to stick to the binary operation in the group. If you're working in Z5, work with addition modulo 5. If you're working in Z8, work with addition modulo 8. If you're working in Z, just work with the usual addition of integers. So always remember which binary operation you're working. So let's consider this is a set, a matrix in the general linear group of degree 2 over the real numbers. So they are real matrices, these ones. So you can get all these powers of A. Remember, the general linear group, the binary operation is multiplication of matrices. Under addition, it is not a group. Addition of matrices, this will not be a group. So the binary operation is multiplication of matrices. So A squared will be equal to this matrix, -1, 0, 0, -1. You can also compute A cubed. Can you confirm yourselves that this is true? So you will get the identity at A4. So the smallest integer such that A raised to 4 is equal to the identity matrix. 4 is the smallest integer, such that a raised to 4 is equal to the identity matrix, and that means the order of a in this group is equal to 4. So we know that this group is infinite. The general linear group has an infinite number of matrices in it. But we have found an element of finite order inside an infinite group. So here is some work for you. You pick the D4. You already have this in your notes. Check each element in D4 and find the order of each element. You also have one more thing to do. You can find the order of this matrix in the general linear group. This should be 3. N should be 3 here, not N. The general linear group of degree 3. So we'll stop there for today. As much as you'd like us to continue, we have to stop.
Yes.
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 Unless there are questions.
Yes. Yes.
There is the audio is not very clear.
Could you kindly share this PDF?
Yes, I will share this, but you have most of this is already in the handwritten notes that I shared. So by now you should have seen most of this. If you have bothered to look at them, then there's also another set of notes I shared. The typed notes that I used to use for the previous classes. I shared. Eugene must have forwarded it to the group.
Okay, we have those notes, but I think, I don't know, for me,
There are 2 sets of notes. There's handwritten, and I recently shared another set of typed notes. But they all complement each other. I will share this as well. What I'm trying to tell you is that you have a lot of material to work with. There's really nothing to stop you from reading.
Okay.
So, and this video will also be available. I'll upload it. Okay, so thank you very much. We meet again tomorrow. Is that